All right. So we have that starting material. You're gonna add magnesium and ether. Then that ketone, which is acetone. And then HCl and water. That was the desired product, and it was not obtained. Okay. What was obtained, you have the following NMR data. Okay. And the molecular formula for that was C7H14. Oh, so what I want you to do is I want you to draw the product that was obtained and add the step that was needed so that you could have obtained this. Mhm.
What's the formula from that thing?
So it's 2 plus 2 times the number of carbons minus the number of hydrogens minus the number of halogens plus the number of nitrogens divided by 2. Okay. All right, let's just start. So what I am trying to do is just, continue to give you these difficult problems that you can see how to work them out. All right, what I would do here is I would actually do the chemistry first, all right? And then I would go back and check the NMR data. All right, so the first reaction, you have Mg and ether. And that will give you a Grignard reagent. We can have an intramolecular reaction. This is a very reactive nucleophile. 1, 2, 3, 4, 5, 6. Okay, so prior to step 2 even happening, prior to you adding that acetone, you're going to have an intramolecular reaction. Where you get a 6-membered ring. Then you add the acetone and nothing happens because you already had the Grignard reaction. And then you add the HCl and water and you get this alcohol. Right. Now what I would do is I would check the NMR data. Okay. All right, so C7H14O, you should see that you have 1 unsaturation. All right, a quintet. That's two hydrogens. It's a CH2 between two CH2s. All right, so the signal is for, okay, is that those two hydrogens, right? And it's split into a quintet because of the two neighbors, of the four total neighbors, sorry. All right. The next signal you have is a multiplet. That's four hydrogens. Okay, so again, so here this means you have equivalent CH2 groups. So it's a CH2 between something where X plus Y is greater than 4. Sorry, is greater than or equal to 4. Then you have a singlet that's 3 hydrogens, so that's a methyl group. Then we have a triplet that's 4 hydrogens. So again, you have equivalent CH2s, and it's a CH2 next to a CH2. Okay, so the signal would be for one of these CH2s, and it would look like a triplet because of the two neighbors. And then you have a singlet that's 1 hydrogen. All right, so I would assume that's the OH hydrogen. So if I make A, B, C, D, E, and then I take my structure, I'll make my structure a little bit bigger. Down here. All right, so this is hydrogen E. All right, the methyl hydrogens would be C. The quintet would be here. The multiplets would be here. And then the triplets would be here. Okay. Does everybody see how I got that product and how the product matches to the NMR data? You will have an NMR problem on this part too this time around. All right. So what did I need to do so that I could have obtained the products that I wanted to obtain? So I would have gotten that tertiary alcohol chain.
Cyclic acid.
Right, you had to protect, okay, the carbonyl. Right, so the sequence should have been, but prior to making the Grignard, adding ethylene glycol, okay, which would have protected the carbonyl, then adding the magnesium and ether, then adding the acetone, and then finally, when you add the acid and water, this is going to protonate the O-, and it's going to remove the cyclic acetal. Okay.
You
Agent.
said first up the acetone is the only thing after the intermolecular reaction.
Correct.
Why is it there?
So because initially, so if you did this and just say you didn't realize to like this is what you wanted to make this, okay? And right, inexperience or not paying attention, either thing, you go in, you make your Grignard, then you add your acetone, you add your HCl and water, like and you don't get what you expect, okay? And the reason is that so you're adding it thinking that you're going to get that red product. All right, but because you didn't protect the carbonyl and now you have a reactive group that's on the same molecule as your nucleophile, you don't have to rely on diffusion. They're right there. So when you have an intramolecular reaction. Think about it from, I mean, the best way I can relate it is your biology, okay? Your proteins, your enzymes are there to position reactive groups, okay? So this way, what takes us, could you imagine if our biochemistry was like what happens in the lab, the hours and the concentrations that it takes to make things? Things happen on a, picosecond to nanosecond time scale in our bodies because an enzyme positions the two groups perfectly so that they can react in that orientation. Right, in the lab, we're relying on heat and random collisions to get things to react. So if you have your reactive group on the same molecule, you're effectively increasing the concentration that you can get rapid reaction that way, okay? So if you didn't protect that carbonyl, then you wouldn't have, that's when you get the intramolecular reaction. And that nucleophile is so reactive that it's just completely consumed. So there's no reaction with the acetone. But once you protect it, now you can add the acetone because that's where you want the reaction to take place, okay? All right. All right, so those are the types of problems, right, to expect on a part 2. And so the question was posed to me at the end of class on Tuesday, if I'm going to give you a homework on this, and I am going to give you a homework on this. And what I'll probably do is in addition to posting a practice multiple choice and a practice test, practice part 2, I'll kind of post like a recitation essentially for you guys to look through. Okay. All right. But now what I want to do is I want to move on to chapter 19. And where I finish is where, not 19, 20. Where I end is where I end, Grace.
Could you show what the NMR would look like for the desired product? Is it different?
All right, so all right, one, you would have way more signals because there's no symmetry here. So in the undesired product, you had symmetry essentially through this carbon. So we had those 5 signals. All right, so here you would have A, B, C, D, E, F. These 2 would be G, and that would be H. Okay, so just off the bat, you'd have an increased number of signals. All right, so will you guys tell me what would be the splitting for A? A singlet. That's 3 hydrogens. What would be the splitting for B? Good, triple, that's 2 hydrogens. What would be the splitting for C? Multiplet. That's 2 hydrogens. D would be a multiplet. That's 2 hydrogens. E would be a multiplet. That's 2 hydrogens, right? What about F? What would F be? A triplet, that's 2 hydrogens. What would the signals for G be? A singlet that's 6 hydrogens. And then H would be a singlet that's 1 hydrogen. Okay, so that's a pretty big difference in the spectrum. All right. So chapter 20. We are looking at carboxylic acids and their derivatives. Okay. The structure of a carboxylic acid, we should know. Okay, we've looked at this functional group before. Right. From the IR perspective, right, you have a carbonyl stretch that's going to be between 1700 and 1725 wave numbers. And then you also have an OH stretch that's very broad. Okay, it's very broad because you can have intramolecular hydrogen bonding. Right, so you could see this type of stretch go from about 3,400 to 2,500 wave numbers, okay, is really broad. The NMR. In the proton NMR, you're going to have a singlet for the carboxylic acid hydrogen that's between 10 and 13 ppm. All right. So, right, I have a carboxylic acid here and I have an alcohol. Again, you have to understand this is a log scale, all right? So that is essentially a factor of 1,000 difference in acidity, okay? Why is a carboxylic acid that much more acidic than an alcohol? Carolyn.
Resonance.
All right, yeah, so resonance. Tommy, do you have something also, or?
Semiconduction.
Yep, okay. So we have several things that are going on here, right? You have resonance in the favor, okay, of the carboxylic acid, right? And we also can have the inductive effect when we add electronegative groups. Okay. And this itself, the carbonyl itself is inductive. We talked about this. There's a delta positive. It's an electron withdrawing group. Okay. All right, what I want you to do is take these pKa values and match them up with the acids that I've listed. All right, so we should see that they go 4, 3, 2, wait, no. Oh, this should have been 8, 2. Okay. And then 1. All right. 1 is the least acidic. You add the electron withdrawing chlorine. Okay, you increase the acidity. If the chlorine is closer, you increase the acidity, and here it's the closest. Okay. That should be review. We did this in the fall, the inductive effect. Your reactions of carboxylic acids. We can take a carboxylic acid, and this was on the exam as well, and treat it with lithium aluminum hydride. And we get a primary alcohol. Okay. And we can no longer use the excuse to me that we had it wrong in our notes, because I'm recording all of your lectures. So if 2 of you have it wrong in your notes, well, and you didn't go back and watch the recording, that's on you. Okay, we have recordings now, so you can go back. So when we have the same work and it's, well, it was wrong in both of our notes, well, go back and watch the videos and make sure your notes are okay. All right. So carboxylic acids will react with lithium aluminum hydride. In the second step, you have to add water. They do not react with sodium borohydride. Okay. Essentially, this reaction is very similar to what we looked at with aldehydes and ketones, okay, where you have a hydride nucleophile. It is a little bit different because you actually will form a leaving group here. I'm not going to go through it with you. All right, but just understand that you get a primary alcohol. So what we're going to do is, and just to review these because they were on exam 1. We're going to reduce this several different ways. All right, so you have an aldehyde, you have an alkene, and you have a carboxylic acid. Right? All of these can be reduced, okay, but they're not all reduced by the same reducing agents. So draw the 4 different products that you would get when you treat this one molecule with 4 different reducing agents. All right, lithium aluminum hydride will reduce the aldehyde and the carboxylic acid. So that you have two primary alcohols. Wait, do I have too many carbons? 1, 2, 3, 7, 1, 2, 3, 4, 5, 6. No, I don't. Okay. All right. H2 over platinum or nickel, right, is going to reduce the aldehyde and the alkene and not the carboxylic acid. If we instead use rhodium, which is less reactive than platinum or nickel, we will keep the aldehyde and only reduce the double bond. And then finally, with sodium borohydride, you only reduce the aldehyde. Okay. All right, so you need to know these selective reductions. The next reaction that we're going to do is a Fischer esterification, right? We will do this in lab, okay, after we're done reacting with cinnamon aldehyde. Okay. All right, you have to know this mechanism. So this is the fourth possible mechanism, okay? You need to know a primary amine to an aldehyde or a ketone. You need to know a secondary amine to an aldehyde or a ketone. You need to know an oxygen nucleophile to an aldehyde or a ketone, right? And so now we have a Fischer esterification. So we're going to take a carboxylic acid and we're going to add an alcohol. You're going to have an acid catalyst. And we are going to make an ester. So just based upon what I drew above, see if you can draw the product. So that is the products that you get, right? What we are going to see is that this oxygen, right, comes from the alcohol. So if I were to put a label on that oxygen, so let's just say I had ETO18H, this is heavy oxygen, okay, it's radioactive. Then I would be able to see that label here. You would see it in the ester, okay? Right, so we're going to go through this mechanism. All right. The carbonyl carbon has a partial positive. The oxygen is a nucleophile. Is it a weak or a strong nucleophile? It's a weak nucleophile. When we had weak nucleophiles adding to carbonyl carbons on Tuesday, what was the first step? What did we have to do, AJ?
Move the double bond to the top of the oxygen.
But how do you do that, Joy? Protonate the oxygen, okay? So we protonate the oxygen. All right, now that we've protonated that oxygen, we have resonance. Okay. So we've made this carbon more electrophilic. There's more positive charge. So now our alcohol or oxygen can act as a nucleophile. And we are going to get a tetrahedral intermediate. So we can deprotonate this oxygen. All right, so this should look like a familiar stopping point. All right, we saw this on Tuesday when we looked at oxygen nucleophiles. We don't currently have a good leaving group, but we have acid, so we can make a good leaving group. So we can protonate one of the OH groups. It doesn't matter which one. So now we have a good leaving group and water can leave. And we have resonance. Actually, I want to scroll and make them all go in a line going down. So you can resonate out to the OH oxygen, or we can have resonance to the OCH3. We can easily deprotonate here. And there's my ester. Right. Right. So if I squeeze the whole thing in, come on. Yeah. There's your whole mechanism, okay? Again, notice the reversible arrows. Okay. Water is a side product. To drive this reaction forward, we want to remove water. We're going to see if we add water and acid, that's how we hydrolyze an ester. Dissolvable stitches are made from polymers of esters. Okay, we have a slightly acidic environment so that we're able to slowly break down those stitches over time. So if we add water and acid, we will break up this ester. Draw the product of this reaction. All right, we can form a 6-membered ring. Okay. Again, this is the nucleophile. There's no change in stereochemistry for that methyl group because it didn't react. It just went along for the ride. Okay. So just like we can have intramolecular reactions for our other nucleophiles, you can have the same thing for a Fischer esterification. We can do what is known as a trans esterification. If you have an ester and you add an excess of another alcohol, and you add an acid catalyst and you remove, well, here you would remove methanol, not water, but I won't include that. You can change out the ester group. Okay. Because again, this reaction is reversible. Hydrolysis, I was alluding to this before. If you have an ester and you add water and acid, you break apart the ester and get back the carboxylic acid. and the alcohol. You only have to know the mechanism from the forward direction of a Fischer esterification, okay? Does anybody have any questions with this? What we're going to do now is we're going to look at what are known as carboxylic acid derivatives. An ester is a carboxylic acid derivative. So here's your carboxylic acid. A carboxylic acid derivative, instead of an OH, you have a different leaving group. Right, so the first derivative that I drew is an acid chloride. We saw this, right, in the aromatic chemistry chapter, right? You had an acid chloride that you were able to convert into an electrophile to functionalize a benzene ring, to acylate a benzene ring. Now I'm going to show you how to make them in a little bit. Here we have an acid anhydride. All right, here we have an ester. We just went through those. What's the last carboxylic acid derivative that I have there with the nitrogen? What's that called? Starts with an A. Not an amine, but an A. Did you say an amide? Yeah, so an amide or an amide, however you want to pronounce it. Okay. All right. What we are going to see is that, again, Y is a leaving group. Okay. So we're going to look at reactions of these derivatives where you have your derivative, you add your nucleophile. The first step is going to be addition. Okay, similar to what we saw in the aldehyde and ketone chapter, similar to what we saw in the Fischer esterification. And you make a tetrahedral intermediate. But now what happens is, because we have a leaving group, we get an elimination, which again is what we saw in the Fischer esterification. These electrons can come down and kick off Y, right? When we did the Fischer reaction, we had to make a good leaving group. We had to protonate. You're not going to have to do that here. So your leaving groups are going to be Cl minus, or carboxylate, and alkoxide, and this negative nitrogen. What we are going to see, which would be, all right, we talked about this a little bit. Your leaving groups are similar to A minus, right? That conjugate. So chlorine is the biggest. Okay, and it's electronegative. It's not as electronegative as oxygen, but it is bigger than oxygen. Chlorine is the best leaving group. Then we have a carboxylate. So this is your carboxylate. And this is your alkoxide. Which is a better leaving group, the carboxylate or the alkoxide? Why? It's not conjugated. What can happen here? Resonance, okay? So you have resonance. So you have a negative charge on oxygen in both cases, but in the carboxylate, you have resonance where there's no resonance in the alkoxide. So that's why the carboxylate, okay, is a better leaving group. Now we have our alkoxide and our nitrogen, okay? This is a better leaving group, the alkoxide. Why? Because oxygen is more electronegative. So do you understand why I'm saying to you that sometimes you have to memorize certain concepts, but then they just carry through? Okay, this is the same thing that we looked at when we looked at the stability of an acid or the strength of an acid. Okay, same principles are applying here. It's not learning new principles. It's just using them in a different way. So your acid chlorides are the most reactive, followed by the anhydrides, followed by the esters, followed by the amides. Okay. I'm going to relate this back to your biology again. All right, think about your biomolecules. Right? What's the function? What type of molecules are the functional molecules? All right, what performs most of the functions? Or what? What are our enzymes considered? What class of biomolecule? It's a protein, right? Proteins have amide bonds. Proteins have to be pretty damn stable, right? Because they have to function. Your nucleic acid, messenger RNA, it's transient, right? It's only there when we need gene expression. So there you have phosphodiester bonds, not as stable. You can cleave up that RNA a lot faster. It doesn't last as long, okay? All right. All right, so how to make acid chlorides. You have a carboxylic acid. And you treat it with thionyl chloride. And we need pyridine, okay? And you're just going to make an acid chloride. Right? If you recall, we saw this reaction in organic 1 when you have an alcohol and you treat it with thionyl chloride, you make an alkyl chloride. Okay? All right. So you don't need to know the mechanism for this. You just need to know that this is how we make an acid chloride. Yeah.
Would you also see like an acid bromine?
Not really. So bromine is a lot more hazardous to use, so you don't really have a thionyl bromide. But it's just from a reactivity perspective. The thionyl chloride is a little bit more stable than a thionyl bromide. Okay. Think about it. You don't brominate your pool, you chlorinate your pool. It's just a little bit more of a stable anion. Okay. All right. So draw the product of that reaction. That's it, pretty straightforward, okay? That's how you make an acid chloride. What we are going to see is that you can take a more reactive carboxylic acid derivative and make a less reactive one, but you can't go the other way, okay? So an acid chloride can be used to make an anhydride. It can be used to make an ester. It can be used to make an amide. Okay. So this is your electrophile. Your nucleophile right, to make an anhydride is going to be a carboxylate. Right, and you will most likely see the counter ion. And then that will give you your anhydride. I'm going to just make that R1 there so that you can see where it added. So this whole thing came from the carboxylate. To make an ester, you just need to add an alcohol. Okay. Here, an acid chloride is reactive enough that you do not need an acid catalyst. All right, the chlorine is that good of a leaving group. And you get an ester. Again, that came from the alcohol. For an amide, you just need an amine. All right, and that came from the amine. So just to kind of give you an example. So draw the product of that reaction. I'll give you one more too. Okay, so the first one, you should get an ester. That looks like that. The second one, what carboxylic acid derivative do I get? What's it called? An anhydride, okay? So not, nothing overly crazy here, pretty straightforward, right? When you do have, when you're trying to make an amide, right, you will see pyridine present. So the product that you get is an amide. Okay. But you need to have pyridine because, right, the chlorine is a leaving group. Right? Notice on this nitrogen, right, you're down a hydrogen. Right? You have to deprotonate the nitrogen at some point in the mechanism, right? And then you have HCl as a byproduct. And that hydrogen can protonate any unreacted amine. So you have the pyridine to soak up the H plus that's produced. Okay. All right, so again, you can just go down the line with these. If you have an anhydride, right, you can convert an anhydride into an ester or an amide. To convert the anhydride into an ester, you use an alcohol. To convert an anhydride into an amide, you use an amine. To draw the product for that reaction, and that reaction. Right. For the first one, you should get an amine, I'm sorry, an amide. The second one, so you have a cyclic anhydride. This acts as a nucleophile and attacks. The electrons go out onto the oxygen. So again, I'm not making you be responsible for the mechanism, but it's the same thing that we've been looking at. Right, so we can deprotonate that oxygen. Now our leaving group can leave. So the electrons can come down. The leaving group is the carboxylate. So that opens up so that you'll have an ester on one end of the molecule, right? So this is going to be that carbonyl carbon 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4. So 4 has a carbonyl, 5 is that oxygen that left. All right, we were able to deprotonate before, so there's a source of hydrogen. And you have an ester on one end and a carboxylic acid on the other. Okay, So it's the same thing that we were doing. AJ.
And it's the cystec problem, for that first one that we did where we got the amide,
Mm-hmm.
is it more important to know what type of molecule we're going to end up with, or the structure of the molecule?
I'm not sure there's a distinction.
Like, say, like, if we do that, we say, oh, I get an amide, like, is that better to know what the actual molecule will look like? And then move from there. And I feel like that's what I did with sometimes like messing up, I don't know.
I think it's important to know what kind of functional group you're gonna make, okay? And how to, I think it's more important for synthesis to know how to interconvert the functional groups. Okay. All right. So those are your conversions, right? You can take an ester and just last, so we can make take an ester,
Can
And-
you scroll back up, like, just, thank you.
okay, and make an amide. And your nucleophile is an amine. Okay,
I'm good.
all right. So I told you that you can hydrolyze an ester using H+ and water. Okay. Well, we can also hydrolyze an ester using NaOH. Okay. When you use NaOH to hydrolyze an ester, it's called saponification. This is one of the ways, right, that you can make soap. So if I have an ester and I add NaOH, understand that this is aqueous, okay, so that there is water present. OH- is a strong nucleophile. I do not need to I don't need to protonate. So I can add to the carbonyl, my electrons go up. I have a leaving group here. It's not the best of leaving groups, but it is a leaving group. So the electrons can come down and we can kick that off. And we get our carboxylic acid. Plus, I want to circle that, plus an alkoxide. So to make that alcohol protonated, NaOH is the first step. The second step of the reaction, we have to add H+. And so that we will get our carboxylic acid and our neutral alcohol. So 2 ways to hydrolyze esters. You do not need to know this mechanism, okay? But you just have to understand that a base, all right, can hydrolyze an ester. I forgot my ON here. So just to let you know, and if I change it up, okay, which I might, when you have and I feel like I've drawn this for you guys before. This is a triglyceride. So here you have glycerol. And here you have your fatty acid chains. These are just simply esters. Triglycerides, all right, particularly saturated ones, okay, are found in animal fats. Okay. This was the basis for soap making. You would just hydrolyze, okay, these with NaOH, and you do not protonate, so that you can keep the O minus, okay, on the glycerol and the carboxylate chains. And then these can form into micelles, okay, where you have the polar head groups. Okay, so there's your negative charges. All right, so that your organic molecules get trapped and your polar molecules interact with the surface, all right? So that's how we make soaps. The last thing that I'm going to do, and then we're going to be done as far as what you're required for exam 2, is if you take an acid chloride, okay, and react it with a Grignard reagent, you add 2 R groups and get an alcohol. So it adds twice. So the first step would be that. The second step would be HCl. So you get addition of R 2 times. Same thing if you have an ester. If you add a Grignard, you get addition of R 2 times. If we take an acid chloride and we just want to make a ketone, then what we can do is use what's known as a Gilman reagent. So where you have 2 R groups, copper and lithium, and then in the second step, you add your HCl. Okay. Your Gilman reagent is less reactive. So you only add 1 R group. All right, I'm going to stop there.